this is the first lecture on panel data models. We, as I said, this is one of two lectures. So next lecture we'll continue with the panel data models. Today, basically we'll look at the basic panel data estimation. But before we do that, let's first have a look at what we did last week. So last week we looked at two topics. We looked at discussed how to model volatility, and we explained how financial series such as stock prices, exchange rate, often exhibit volatility clustering, where we have periods of turbulence or periods of more like calming. So when you look at how the series behave over time, you'll see this such a volatility over time. To measure volatility, we should also, if we use the unconditional variance, this is a number, just a single number of a given sample, which wouldn't show the or capture the time varying volatility, and that's why we use electric shock. And that's why we use the ARCH model. So in financial data in general, we have this autocorrelated heteroscedasticity, and that's where the name comes from. So ARCH effect or ARCH effect. So this is autocorrelated conditional heteroscedasticity, and what that means is if we have a series YT, if we model this series based on or conditioned on information in the past up to t minus 1, then the error term here again would condition and it or an information up to t minus 1 will be assumed to be normally distributed, but with a variance that is sigma t squared. So the difference here is that we have this t subscript here. So we usually what we'd expect in this sort of estimation to have constant variance, which means homoscedastic errors, but in this case we have heteroscedastic errors, but because the variance is autocorrelated over time. So this is where it comes from. So in this sort of setup, what we do here, we take into account the ARCH effect by letting the variance change over time, or depending on the time, because it's autocorrelated over time. So in that sense, then the sigma t squared will be depend on a constant lambda 0 plus lambda 1 ut minus 1 squared. That means, I mean, this is ARCH 1. So when you consider only one lag, but you could actually extend the model to up to p lags. So in this case, we have the first lag, the second lag, up to the p lag. We can test for these coefficients, whether they are statistically significant or not. If they are, then this is evidence we have ARCH effect, and this is something that we need to consider or to account for in the model. If these coefficients, these lambdas, are found to be not statistically different from 0, that means we have no evidence of ARCH effect, and that will make this sigma squared, so this sigma t squared is equal to lambda 0, which means this is likely to be like homoscedastic error, and this is the usual way how we model this. And but if these are were found to be statistically significant, that means that we have ARCH effect, and we should keep this in the model. We should account for this in the model. We also showed that GARCH11, which again, this is an extension of the original model, the ARCH model, is equivalent to ARCH P. So if we have, as P increases, so empirical evidence show that if we have more than ARCH3, so if we were to go back in the past more than three lags, then it is actually better to estimate GARCH11. And the difference here, you'll see the error term again. So you will have the same structure here of the ARCH model. So the first part of this first two terms here, lambda 0, lambda 1, ut minus 1 squared. This is ARCH effect. This is the same equation we had in the previous slide. But what we add here, we add the sigma t minus 1, sigma square t minus 1. And again, this is one lag back. So usually we could extend this as well, gosh, to include more lags. But in most applications, we found that gosh 1 should be sufficient. And the advantage here of having gosh 1 is we rather than estimating p plus 1 coefficients, we actually want to, we have only 3 coefficients to estimate. We show also that gosh model we can extend to have gosh m, where we modify the mean equation by explicitly including the conditional variance into the main equation as a measure of risk. So we include also the risk factor in the mean equation. So that was the first part of the lecture. Then we moved to discuss economic forecasting. And basically what we did, we discussed 2 methods how to do economic forecasting using a regression model, and then we discussed the ARIMA modeling. In the first part, or the first method of doing this, we learn about many terminology that are useful. We learn the difference between point and interval forecasts. We learn about the estimation period, ex-post forecast period, and ex-ante forecast period. And if you remember, we had an example of the exchange rate for the euro against the US dollars. And I think we had data up to 2008, but what we actually used for the estimation was 2004, and we kept the last 4 years, the data from the last 4 years, and that was the holdover sample, and we explain why we need to do that. We want to evaluate the performance of the estimated model, then we can build on that, we can judge, we can see whether we can use this model or not, whether it is a good model to use or to be used in forecasting or not. And then we learned about the conditional forecasting and the unconditional forecast. So if you remember, when we with the conditional forecasting, we kind of build some scenarios of what happened in the right hand side, the regressors, and then we try to forecast based on this. We try to forecast the value of the left hand side variable. And again, we learn how to calculate the forecast error, and we want this to be as small as possible, because this is an error. So the second methodology we discussed last week was the Box-Jenkins methodology, or ARIMA methodology, which has 2 components here. So it combines AR process and MA process, autoregressive and moving average process. And these are, so YT depends on YT minus 1, YT minus 2, up to YT minus P. And the main idea here is that with ARIMA modeling, the idea here is that you use the data to explain the series to explain its own behavior. So you use information from the past about YT to explain what YT or how YT is going to behave in the future. So that's what we do. So you need to be very careful about constructing them, and we see the steps now, the identification, how many lags I should go back in the past in order to have a correct model. It's something that you will never be sure about, but again, we'll show some diagnostic tests how to test for that. This is the MA process. This is the error term in time t there plus the error term in time t minus 1 up to t minus Q. And as we explained, the Box-Jenkins methodology assumed that data, the series YT here is stationary or could be made stationary by differencing, and that will make it from ARMA to ARIMA. So ARIMA here, I here, or the D here is the number of times that you need to difference this series to make it stationary. And again, so these are the 4 steps, as I said. So the identification, you need to determine the appropriate length, lag length. So the values of P, G, and Q. So this is the lags for the AR process. This is how many times you need to difference the series to become stationary, and Q is the lag number, or how many lags included in the moving average process. The estimation, then you estimate the parameters. Then you need it's very important to do diagnostic checking. So you want to make sure that you've got the correct model, you've got a good model that you can build on, that you can use in forecasting. And we explained this is sort of art more than science. So you actually have to try different specifications, different models, and then you compare. And then you decide which one is the best model that you can use for this purpose. So the idea here is that how to check that. So you need to look at the residuals. You need to check the residuals. And again, if they don't satisfy the assumptions that we made around the residuals of the model, then again you will have to start again and again until you find a model that you feel is the best performing model, and that one you will use in forecasting. So when you do the forecasting, you do it within sample period and outside the sample period as well. We also compared the static forecast with the dynamic forecast, and we explained how eViews actually made that easy for us now with the automatic ARIMA selection, where it actually evaluates a large number of models, and then it gives you, based on the information criteria, it gives you which one is the best model and which and why, and probably you could use that to help choosing or choosing a good model. And again, so there's no way. You will never know the best model, so you're just trying, and it has to be something that you need to decide on as well. But that will usually happen when you have few models and you compare and you see which one is performing in the best way that you can have, and then that's the one that you will use for forecasting. So as I said, so we give a few lectures on time series econometrics. Now we are going to move to a different sort of models or data, how we treat this data, which is panel data. So basically, this is the sort of data we've been dealing with. This is just an example of time series data, and this is how it looks like. So we've got data for one unit. The unit here is a country called Egypt, and the over years. So we've got that. We got data for X and Y over time for the same country. So if you look at the cross-section data, then we have a number of countries, a number of units, but at the same point in time. So we got 2000. So we got data for X and Y at the same point in time for a number of subjects. These subjects could be countries, like the case we have here, could be individuals, could be firms, could be any subjects. Okay, so or any entities. So you can include anything, but again, we have the data only for a single point in time. So this is the difference. But when we have panel data, which we're going to explain today, so we will have data for a number of units, a number of subjects, like we see here, Egypt and USA, over time. So from 2000 to 2004. So we've got data for X and Y, these two variables, across countries. So we have different countries here. We have different units, and also we have the data over here. So obviously, what we have here with panel data, we got both elements together, the time series and the cross section. And you would expect that the problems we used to have or we used to face with time series econometrics to exist here, because we have the time element, and the issues with the cross sectional is likely to be here as well. So some of the issues will be here as well. But there are ways to deal with this, and that's why we're gonna cover today and next time. So this is the nature of panel data as we explained, but to introduce this in a more formal way. So what we have here, when you collect data for different objects over time, as we explained, but this is how you formally introduce or explain or present a panel data model, where we have here YIT, the dependent variable here. So I is just the unit identifier, T is the time, so in time T, and the same thing with on the right hand side, the regressors or the explanatory variables, the same thing. So you collect data across individuals or across units and over time as well. The intercept here is constant. This is we used to call it beta 0, and as I said, X, IT, or these are the parameters that we need to estimate, and these are usually K k by 1 vector of parameters to be estimated. So the data here goes from 1 time t equal 1 to t, so and from I equal 1 to n. So this is how to present it more in a more like formal way. But why do we need panel data? Why do we need to do this? Why do we need, what are the advantages or what are the benefits from using panel data? This is a very important question, because with if we go back to the cross-sectional data, so the form of the example I just showed, one of the things that we don't capture, and this is the heterogeneity among units, how these units are different from each other. With panel data, we actually can explicitly model such heterogeneity by including subject-specific variables, where if you want to, if you look at the sorry. So if you look here, so you've got Egypt, USA, so a number of countries here, yeah? So how different these countries from each other, how heterogeneous this group is. So if you look at the income per capita, if you look at the population, if you look at the geographical location, if you look at the culture, religion, so many differences. So it's very heterogeneous group. Okay, this is not captured explicitly, but it would be captured, or it can be captured explicitly in. Sorry, just get electric shock from my laptop and this pointer is not working. So anyway, so going back to the point, yeah, the importance of panel data. So why we need panel data, why panel data is important. As I said, we can take heterogeneity explicitly into account by allowing for subject-specific variables. It's very informative because rather than looking at one subject over time, as the case with time series data, or looking at different subjects at single point in time, you actually have the 2 dimension in your data. So you have time and units. So that gives you more information how your variable of interest behave, not just over time or not just across units, actually both. So units, and so it gives you more information. It's more informative, and also you will have more variability, less collinearity as well, because you could have 2 variables collinear at some point, but actually if you look at this over time, or if you look at this across different units, it might not be collinear. So the chances that you will have multi-collinearity will be probably less. Also, one important, like if we talk about empirical research, one of the important thing is the more degrees of freedom, because some variables such as like some indices like corruption index or different governance indicators, they actually started since like probably 1990 something. So if you look at, for example, an index that is started from 1995 or 1998, and that's an annual index. So if you want to construct a data set for one country or for one unit, based on that, you will have 20 data points. So 20 data points as time series format. So then probably you wouldn't get a very meaningful statistically, I'm talking estimation. But when you have 20 data points times 100 units, if you're looking at 100 countries, so that would give you 2,000 observations. So you see the difference, how it allows for more degrees of freedom, give you more data points, and actually that would allow you to add more variables and more parameters that you can estimate, because every time you add one more parameter, you're actually sacrificing 1 degree of freedom. So if you don't have enough degrees of freedom, so sometimes even the estimation is not possible, or is not meaningless, it's not meaningful, sorry. Okay, so one of the benefits of having panel data, again, it actually allows for more degrees of freedom, which is really good especially for people who work with data that is not available in like doesn't have a long time component or a long time element. So again, it allows also for the study of dynamics of change. So rather than looking at how the variable behave just over time or across sections, you actually look at this over time and cross section as well. So you look at, so this explains the more the dynamics of the data in hand or the variables of interest. The last one, by constructing the model in an appropriate way, you can actually remove the impact of certain forms of omitted variable bias, which specifically those variables that are subject specific and you can't measure. So these don't change if they don't change over time, and in the same time you can't observe them or you can't take them into account, so the impact goes into the error term. So I'll show you now when we estimate panel data how we can actually get rid of this effect on our estimation. So it actually reduces this sort of omitted variable bias again. So the problem comes from if you drop a variable, or if there's a variable that you can't collect data for, or the variable that you can't measure, or the variable that you can't observe, so that impact goes always to the into the error term. Okay, so this will cause omitted variable bias. Okay, because this sort of effect is in the error term. But if you have a panel data, and if you do, for example, like and again, if this sort of effect doesn't change over time, and it's subject is specific or unit specific, so it's related to this unit. So if we're talking about country, if it's something related to culture doesn't change really over time. It doesn't change very quickly. So it's probably over the last 20 years, it is something that is constant, that doesn't change. But again, you can't capture it, you can't measure it. So the impact goes into the error term. So with panel data, if we construct the model in a certain way, the way I'm going to show you in a few minutes, you can actually get rid, or you can reduce the sort of bias. Okay, so we understand now panel data is important. Panel data give us more in terms of what it offers, in terms of capturing or explicitly modeling heterogeneity, looking at the change or the dynamic of the change, or look over time and across sections. It give us so many benefits, give us more degrees of freedom, and etc. So the question here, the important question, how to estimate panel data. So what we discussed before, we based our discussion on OLS estimation, ordinal least square. So with panel data, how can we estimate this model? How can we estimate the parameters here, beta? Okay, so one way to do it, or the simplest way to think of that, is just to ignore the fact that you've got a panel data, and that's what we call pooled regression. So what you've done here is that you pool all this data as if they are just one sample or one. So you ignore that you have both elements, the cross section and the time element. So and you estimate the model using ULS. But the problem here, and that's probably a serious problem, that you actually losing so much, because you could model heterogeneity, you could model how these units are different from each other. Okay, so with this sort of modeling, where you ignore the fact that you've got the two elements in your sample, the data and the units, and you use OLS for estimating this, to estimate this model, which we call the pooled regression, you're losing so much information because you could actually capture this sort of heterogeneity, and that's something that we lose if we use pooled regression. We still can use it, but I'll show you in the example at the end how we compare between the estimates from these two different models. So another way to do it then, with pooled regression, we've got a problem of not being able to capture heterogeneity. Then how would we do that? How could we capture heterogeneity? So the difference between the model you've seen now and the previous one is this term is mu I, And mu I here, that is a variable that capture all variables that affect the dependent variable yit cross-sectionally but do not vary over time. So things that are subject specific, but they are constant over time, so they don't change over time. An example I just gave in a minute ago was about culture. So we say culture, it doesn't really, if we capturing or if we're modeling, or if our units are countries, so countries, the geographical location, for example, it is something that is not going to change over time. It's very country specific. It is related to this country. Okay, so and this is and so on, and this is sort of the heterogeneity we're looking at. Another example here, for example, the sector that a firm operates in. Again, this is something. Is not expected to be, or to, it is a firm specific, it is specific to this firm, but it's not going to change over time. So think of this mu I also as like a person's gender. So if we're modeling, if our subjects are individuals, then the their gender is probably something that is very specific to them, is not going to change over time. And so on. So that different ways you can think of this, but again, this variable is gonna be like a catch-all heterogeneity stuff. So anything that is very specific to these subjects, to the units in this model, should be captured by mu I, and this would through allowing different intercepts for each cross-sectional unit. Because so if I here, for example, country 1, so the first country, then the intercept for that country will be equal to alpha plus mu 1. So that is specific element for that country. If this is, but again, this constant or this intercept is not going to change over time. Okay, because this is a fixed number, this is a fixed number. So actually, when you add these together, so it's a constant, but its constant is specific, is related to country 1. Okay, but again, country 2 will be alpha plus mu 2, and so on. And these are country specific, if I'm talking about countries, and these are not going to change over time. So they are constant, but they are constructed for, or by definition, these will be for each one of the cross-section unit we have. Okay, in my example, I'm looking at countries. You could be looking at firms. You could be looking at individuals. So it doesn't matter what sort of units you're looking at. You will always have some subject-specific characteristics that you want to account for, and that is the source of heterogeneity that you can't capture with other models. So here you actually looking at this very explicitly by adding this mu I. So this, you allow for different slope for each, different intercept for each cross-section unit, and this will not vary over time. But still, how are we going to estimate this? One way to estimate this, so the question is, how are we going to do this? Fixed, that's what they call fixed effect model, by the way, so something I should have started with. So this is different from the pooled regression, which we saw here. So the pooled regression, again, we ignore the fact that we have both elements, both dimension in the data set. So we ignore the fact that we have time and cross-section units both together in the data set, and we just did the estimation, but we lost so much information about heterogeneity, which we could capture, or we could explicitly model. But in this fixed effect model, we introduced this sort of heterogeneity, or trying to, no, we didn't introduce heterogeneity, sorry. We're trying to capture this heterogeneity. Heterogeneity was already there. So we're trying to capture it through the introduction of, or introducing this mu I, or different intercept for each cross-section unit. But again, how are we going to do that? That is the question. What are we going to do then? So one way to estimate this model is to introduce different dummy variables. So for each cross-section, you have a dummy variable. So if you have 30 units, and these units, let's say if you have 30 firms, then you introduce a dummy variable for each one. Okay, so we've got 30 dummies. Okay, obviously, if you have a constant, you would have to have 29. Do you remember? Do you remember the dummy variables trap? When we talk about perfect multicollinearity, so if you're introducing dummies, then you should, if you have a constant, you should introduce G minus 1. G is the number of groups you have, so if we got 30 countries or 30 firms, then, and we have a constant, then we should introduce 29 dummies that represent these countries or these units, and the one that we dropped will be our benchmark or our the one that we gonna compare with. But in the equation we see here, there's actually n dummies. So this is the number of groups. But if you look at the setup of the equation, you're not gonna see the constant. So there's no problem in this. That's what I'm trying to say, okay? So if we get n dummies here, I dropped the constant, so there's no issue with this sort of setup. So if we look at the first dummy, D1, again, it's very straightforward to define this. So this will take the value of 1 for all observation on the first entity. The first entity here could be, again, could be a country, could be a firm, could be an individual, could be whoever. So it depends on the subjects you are dealing with. And 0 otherwise. So this is just a dummy variable. So take two values. It take either 0 or 1. So 1 if this was the first country or first entity or the first subject or the first individual or the first firm, call it whatever you want, and then 0 otherwise. The same thing with D2. D2 is a dummy variable that again represent or takes the value of 1 for the second entity and 0 otherwise, up to Dn. So this is the n here, remember, n here is the number of cross-section units we have, is the number of subjects we have in the data set. So if I go back to the first slide, you will see that I moves from, takes the value of 1 to n, to capital N. N here is the number of units, the number of units or the number of cross-section units we have. Anyway, so we'll have n dummies here, okay? So if it depends how many units or how many subjects you have in your data, and by doing so, we actually capturing this sort of heterogeneity, okay? So the that's one way to do it. So, and how would we estimate this? This is a very basic model that we actually can, very straightforward, we can estimate using OLS. Okay, so again, so this is exactly the same model. So we can use this, we can use OLS to estimate this model. So the story is very straightforward now. So we get 2 dimensions in the data. We got panel data, we got the time element and the unit or the cross-section unit. So one way to deal with that is to ignore that fact and then use pool regression. And we said that we're actually losing so much. This is likely to be a misspecified, to be honest, a misspecified model, because you actually ignore that sort of heterogeneity. And panel data allows you to capture this by introducing the mu or mu I, the term that we show. And to do this in a more like practical way, how would you estimate this? You could add, or you could introduce dummies for each one of the cross section. But there's a problem here. It's not a big problem, but there is a problem. Or it is not really, sometimes when you have a large number of n, so a large number of cross sections, then that will require estimating n plus k. K here is the number of, remember, x here is k by 1 vector of variables. This one, the beta is k by 1 and x is k by 1. So k here is the number of regressors or the number of explanatory variables or independent variables. So if you get 10 variables in your model plus 100, so they get 110 parameters to estimate. So again, that is not really, sometimes it's not really helpful if you don't have enough degrees of freedom for that. But anyway, but the idea here is, again, to avoid this, there's a way to transform the model to avoid estimating n plus k parameters. So what which we call the within transformation, or we call it within group estimator. How would we do that? So again, this is another way to estimate the same model, the fixed effect model, okay? But we just transform that model in such a way that we are not forced, or we don't need to estimate n plus k parameters. And the way to do that, if you get the time mean of each entity, so if, for example, this is yi, so this is the average or the mean value of yi, so this is for country 1, for example, and then you get the average for this data for across time, so from t equal 1 to t, and then you subtract the time means from each variable, then that will give you what we call the d-mean variable. So you took the mean away, so you actually subtract the mean from each value. So then you do the same. So this is for y, so you should do the same for x as well. So you do this for all variables in your model. So how this is going to help us? First of all, again, just we're trying to avoid having a large number of parameters to estimate n plus k, okay? And by doing this, what will happen here when you d-mean the variables, you do this to the entire equation, all these dummies will drop, okay? And also your regression in this case is not going to require an intercept, so you're not going to have beta 0 or alpha, because the dependent variable now have zero mean by construction. That's when we d-mean the dependent variable. So then the mean value was expected to be 0 anyway. So that's why we don't include the constant in this equation. So let's have a look how that looks like. Yeah, so this is the new model then. This is the Wheaton transformation, remember? So what we're trying to do here to avoid estimating a large number of parameters or n plus k, doesn't matter how big that number is, but this is a way to avoid estimating all these parameters, is to estimate the Wheaton group estimation, or to do the Wheaton transformation. And the way you do this by demeaning the variables, and this explains. So this is yit minus y bar I. This is the mean value for I, and you do the same thing for x. And as you see, all the constants here drop from the equation. So all these dummies, all these intercepts, so there's nothing there. It's just the vector of x and beta, and the same here with the R term. So this represents the new equation, or the new model, or the Wheaton transformation, where the double dots above the variables, this denote that these variables are demeaned. Okay, so following this process. So again, this can be estimated by OLS in the usual way. The only difference is that we need to make some correction for the degrees of freedom, and most software today would do that for you. So it's not an issue. So you can use the Wheaton transformation to save you the need to estimate n plus k parameter. But again, we're still looking at the fixed effect model, okay? And that is the main idea. So what happened to the fixed effect term, the country or the subject specific term? What happened to this term here? This where is it? This mu I. What happened to this when we do the follow the Wheaton transformation procedure, or we do the estimation for the Wheaton group estimator? So it would drop, because this is constant. Remember this, so all the constants term here in this equation, these will drop. And actually, that is the main idea here. When you do the Wheaton transformation, we're trying another way to estimate the same model, the fixed effect model, but without having to estimate n plus k parameters. N here is the number of subjects, the number of countries, the number of units you have, the cross-section units, plus k is the number of regressors you have. Okay, so to avoid this, we do the Wheaton transformation in this way by demeaning the variables. And when you do this, you actually drop all the constants, you drop all these time invariant variables, these all drops, and then what is left is what you have now, and that's how you can estimate this model. And this is very straightforward using OLS again, and we'll see an example in later on in this lecture. Okay. So another way, again, we're still looking at the same fixed effect model. We're trying to consider different ways to estimate the same model. So we're looking at this alternative to demeaning. Rather than demeaning the variable, you can actually run a cross-sectional regression on the time average values of the variable. So you look at, you actually calculate the average over time for each cross-section, and then you run the regression using these time average one, and this one is called the between estimator. So the previous one was the within group estimator, for the within transformation, and this one, so with the within group, so you're actually demeaning the variables. So you demean your variables, dependent and the independent variables. But with the between estimator, what you're actually doing here is that you running a cross-sectional regression on the time average values of the variables. So one advantage here probably is that with the between estimator, so the averaging process here that we do with the between estimator, this is likely to reduce the effect of measurement errors that we may have in the estimation. So again, it's just a different way to estimate the same model, the fixed effect model. We'll see an example today how to do this. Another way to do it, which we can use the we're looking at the same the fixed effect model, where we introduce where we're trying to capture heterogeneity by including the mu I, this term that capture all these sort of subject specific variables or subject specifics that are constant over time. So it is very specific to that value, to that unit, to this subject, or to this country, or to this firm, or to this individual, depending on your data set, and then it doesn't vary over time. So another way to do this, which actually help you again to get rid of this term, which is mu I, is the first difference. The first difference, if you introduce the first difference operator on the equation, so you're actually looking at the change in y rather than modeling y itself, because it's going to be yit minus yit minus 1. So you actually subtract this from last year, or the time t minus 1, and so on. The same applies to the variables in the right hand side. And when you do that, then you'll end up with change in m in mu I. So what's the change in mu I? It's a constant. There's no change, 0. So you actually drop it. Okay, and that's one of the problems, because any variables, not just mu I, any variables that don't change over time will cancel out. So will drop from the equation. Okay, so if you have any variables in this sort of in the first difference estimation, that means you're actually dropping these variables. So if you have any like gender or any characteristic that doesn't change over time, it will drop, because what you're looking at here is the change in yt. So you're modeling not the behavior of yt, so you're looking at the yt minus yit minus 1. So we're looking at the first difference. So first difference and within group estimation that we just discussed will produce identical estimates if we have only two time periods, if t equal 2. So just let's slow down. Okay, so where the story started from, we're having panel data where we have the 2-dimension. We discussed that we got so many advantages of having panel data over just looking at the time series or cross-section separately. That's one thing. So one way to estimate the model is to do the pooled regression, to pool all this data, to ignore the fact that you have the 2-dimension and use all this, and that's what we said. We actually lose so much information. We lose that possibility of being able to model heterogeneity. Okay. So we looked at the first the fixed effect model, where we introduce this term mu I, which represent all the subject-specific characteristics that don't change over time. So they're very specific to that subject, but they're not going to change over time. So that these are represented, or the effect of this sort of characteristics will be captured by this mu I. How would we estimate this? One way to do this is to use the dummy variable, least squares dummy variable, LSDV, least squares dummy variable, where you introduce dummies for each unit, for each one of your subjects. Okay, and that's very straightforward using OLS. So it's very easy to estimate that, because you just get a n number of dummies and then plus k parameters. And but the idea is, or the issue here is that you will have to estimate n plus k parameters. If you would like to avoid that, there are some transformation that you can make. So in order to deal with this, or to drop these these dummies, okay, or this mu I. So one way is to do the within transformation, between transformation, or the first difference. You can, with the first difference, you drop it actually again. So it's the same way. Okay. So in a similar way, we could actually think of events or things that affect, that are not unit specific. They're actually time specific, meaning, so what we did so far, we looked at the entity fixed effect. So we tried to model it, to explicitly account for the heterogeneity based on these units. They are different individuals, different countries, different groups. So we tried to capture this by introducing the mu I, okay, that term mu I, which represent the subject specifics. So there could be also time fixed effect model, where we try to capture the effect of any changes that happened over time. So it's very specific to that t, so to this year, or to this quarter, or to this, depending on your data set. So in that case, if you think of the YT, when it changes over time, but not cross-sectionally. So it's something that would affect all units at the same time, or in similar way. Okay, so that in that case, we would have intercepts, will allow for intercepts that vary over time. You remember mu I? Mu I was, it varies over cross sections, but it's constant over time. So it has I. So I, these are units, so it change with units, but it's fixed over time. Okay, but this one, we will have intercept that is, which is lambda t here, that varies over time, but it is constant across entities or across cross-sections, cross-sectional units. So it's not going to change, because that when this something change in t equal 1, or t equal wherever, so in the first year and the second year, so it actually affects all units in a similar way, at the same time. Okay, so lambda t in this equation here, lambda t in this I remember this is time fixed effect model, where we introduce this term lambda t, and that is a time varying intercept. So the intercept here, so let's think of this the same way. So y1, so we're looking at the first subject or first unit. So the intercept for this would be lambda in time t. So it would be lambda, alpha plus lambda t. Okay. What about the second subject, subject 2? So y2t will be the same, because it doesn't change cross units. It will be, again, it will be alpha plus lambda t. But if you look at yit plus 1, that will be different. So it will be alpha plus lambda t plus 1. Okay, so this will vary over time, but it's constant across different units. And as I say, this capture all variables that affect y, and that vary over time, but are constant cross-sectionally. If you want to think of an example, if you think of the regulatory environment or tax rate changes, this may influence all firms the same way. So it will influence, yes, y, your dependent variable, but again, the same way will affect all firms. So if you have a tax rate change, this will affect all firms. the same time. So this is something that happen in t equal plus whatever. So, and again, that will give us different, so that will allowing for different intercept, or these intercepts to vary over time, but not across units. Okay, so the how to estimate this in a very similar way, the same way we did with the fixed effects model. We can introduce dummies. So these dummies here doesn't represent units, they rather represent time. So this is t, so this is this will equal 1, d1 t will equal 1 for the first year. Okay, d2 will equal 1 for the second year, I mean 0 otherwise. Okay, and so on. So it's very straightforward. And again, we can estimate it the same way we discussed with the fixed effect model. So time fixed effect model is very similar to the entity fixed effect or subject to fixed effect model. In that sense, we just introduce dummy, or we allow for intercept to vary either across entities if we're looking at fixed effect model, or if you're looking at time fixed effect, you allow the intercept to vary over time. So we already explained this. Again, if you want to avoid estimating a model containing all t, capital T, here's the time element, how long your data is. If you want to avoid this, then you can do similar transformation. So you can follow within transformation in the same way to subtract the cross-sectional average from each observation. So in a similar way, we can do the within transformation. And also, it is possible that you could introduce these dummies that or allow the intercept to change over time. And also you can introduce the entity fixed effect where we have mu I, so you have some subject specific and some time specific component, and in that way will in the same model, and this will be a two-way error component model. But again, the idea is very simple, where you're trying to capture the heterogeneity across units. You introduce mu I. This is a fixed effect model, or entity fixed effect model, if you wanna call it that. So, and also you could do the same with time, because we could have something specific to this time, so we can allow the intercept to change or to vary over time, but not across units. But also we can have both together in the same model. Okay. Any question? So far we in the first model, the fixed effect model, we assume that we can capture the heterogeneity by introducing mu I, and mu I this will be like a subject specific term. There's another way to look at this, which is the random effects model, or sometimes known as the error components or the composite error components model, where different intercept terms for each entity. So it's the way we model this intercept. So just if you think of this, we looking at how we model the intercept in all these models, how the intercept works, how we model these heterogeneity. So in the random effects model, we still have different intercept terms for each entity, and these intercepts are constant over time. But what we have here is this error term, the composite error term. So this error term, omega it, equals epsilon I. Look, this is not the constant mu I. This is a random variable. This is something that is random, and that's why it's called random effect model. So the way is this determined, this epsilon I, that's why it's called the random effect model. So now the intercept will be, or the new intercept will be alpha plus, so some part which is common across all units, okay, because you don't see any intercept here, any subscript with alpha. So it is a constant across units and across time, so over time. So but for any unit, so if we look at for any given unit, like unit 1, I equal 1, then the intercept will be alpha plus epsilon 1. Epsilon 1 here is, again, this is determined randomly, so it's not something that, so it's the way that this is determined, or the intercept. So epsilon I here measure the random deviation of each entity's intercept term from the global intercept term or the common intercept term alpha. So alpha is a common or global intercept term, and then epsilon I show you how the intercept for a given unit goes away from this alpha, from this globus, because it could be above or below, it could be more or less than alpha, depending on the sign of this positive or negative, this term. So this is the again, this is the same model. So the idea here is that we don't have dummy variables to estimate this model. Okay, so no dummy variables to capture the heterogeneity, but rather this heterogeneity is captured via the random this part of the error term, which is the epsilon I. So this component that determines that should capture, or is expected to capture, the heterogeneity in the cross-sectional dimension. Okay, so rather than have mu I, but we still have this, but it is epsilon I. Epsilon I is just randomly determined, so it change in a random way, in a randomly fashion. So, but there are some assumptions, okay, if we're going to do that. So again, just the main advantage here, we don't have those dummy variables. We don't have to estimate all this number of parameters. So, but these assumptions have to be fulfilled first. We need to make sure that this new cross-sectional error term, the new one that we introduced, epsilon I, has zero mean independent from VIT, this one, the other component, the other part of the error term, and also it should have constant variance. It should be independent from all the independent variables. Okay, it shouldn't be correlated with the other explanatory variables or the independent variables. So for this to be valid, then we have to make sure that these assumptions are valid too. So the idea here then, how are we going to estimate this model? So with the fixed effect model, we introduce the dummies, and then we could do the transformation, and then we can estimate the model. But with this case, then the all-list parameters, the all estimation of these parameters would be consistently estimated, but inefficient. Okay, and then the way we deal with this, or most software would do that, they actually use what is called the generalized least square method. Okay, so the random effect model is not estimated by OLS, and that's the reason why, because as I said, if we use OLS model, these parameters will be estimated consistently, which is okay, that's fine, but will not be efficient. So OLS are not going to be blue. That's what we want in OLS estimation. Remember the first lecture? That's what we discussed. So if that is not the case, then there's a problem here. So we need to, that's why in most softwares, and I'll show you today, in eViews, how eViews uses generalized least square rather than ordinary least square to estimate this. And it's just very quickly, the transformation involved is to subtract the weighted mean of the YIT over time. So it's very straightforward with software today, because actually it does this for you, so you don't have to worry about it. But you should know that the estimation procedure for the random effect model is not based on OLS, it's actually GLS, generalized least square. Okay, so which one to use then? We looked at the fixed effect model, and how to estimate a fixed effect model, what it means, and etc. And we looked also at the random effect model. So which one should we rely on? So what you see here is the random effect model. So the random effect model is more appropriate if you believe that the entities or the subject have been randomly selected from the population. So that means this epsilon I will be random, okay? And that's how, and that's when the RE or the random effect model will be more appropriate. And also one advantage of using that it will not remove the explanatory variables that do not vary over time. Remember when we did the transformation, the within or the fixed or the first difference transformation to estimate the fixed effect model, we said that those variables that don't vary over time will drop. Okay, so one advantage of having the random effect model, or one advantage based on what we may prefer the random effect model, is that the explanatory variables that don't vary, that are time invariant, will not drop from the model. We have fewer parameters to estimate. So if you compare this with the least squares dummy variable, so you will see that we've got only these alpha and beta k. It could be any number of regressors, so that means k plus 1. So we have k plus 1 parameters to estimate in the random effect model, while in the fixed effect model we would have, do you remember, n plus k if we didn't do the if we didn't do this the transformation. So we did the transformation, but it came at a cost. The cost is that we will drop the variables that don't vary over time. So if you want to do this, if you want to estimate the variables that, if you want to estimate these parameters that are associated with variables that don't change over time, then you will have to use the least square dummy variable, and that will require that you will you estimate n plus k parameters. So again, one of the advantages, as I said, and that's why random effect model would maybe, it's not always the case, by the way, but they may be more preferred over the fixed effect model, is that you would need to estimate fewer parameters, and that means it saves you degrees of freedom, because again, so the more parameters you add, the more degrees of freedom you lose. And then if you have a model that like the random effect model, and you compare it with the fixed effect model, that allow you to save some degrees of freedom by requiring the estimation of fewer number of parameters. So if these are the case, then we expect the random effect model, just giving that all these conditions that we discussed in the previous slide applies or are valid, then we expect that the random effect model will be more efficient or produce more efficient estimation than the fixed effect model. But this is not always the case. Why? And this is why. Because we explained that random effect model is valid only when this omega, which is the composite error term, this part, okay, is uncorrelated with all the explanatory variables. And this is very stringent, or is an assumption that is more difficult, because sometimes you will, or this requires that these both components are not correlated. None of these both components will be correlated with the regressors or with the explanatory variables. So if any of these components are correlated with, or this one correlated with the explanatory variable, then the random effect model will not be the preferred one. Okay. So so this is just an example, like, or explain again why we, in some cases, the random effect model wouldn't be the preferred one if we have unobserved omitted variables, and these were allowed for by having a different intercept for each entity. That was in the That was in the fixed effect model. These must be uncorrelated with the included. This part. If it was mu, it's not correlated with the explanatory variable, but with the random effect model, this could be correlated with the explanatory variables. So the bottom line here is whether this is correlated, any of these two components correlated with the x. Okay, if so, then you should use the fixed effect exactly. If not, then random effect is more preferred. Okay. Okay, so we can use Hausman test. We'll see in a minute. We can use Hausman test to test whether this assumption is valid or not, and based on that, we can decide which one is more appropriate. Is it the fixed effect model or the random effect model? Let me just go quickly then to an example, because I think that would make our life easier. So now we said what we should cover. We looked at what we mean by panel data, how to estimate panel data, what it means a fixed effect model, what we mean by the least square dummy variable method, what it means the within estimator or the within transformation, the first difference, and what we mean by the random effect model. So let's now look at an example. And the example we have here, again, the data are on Blackboard, the data on table 17.1. And this example was trying to model the charitable giving, and what are the factors, what are the determinants that make individuals pay more as charity, for charity. And what the data we collected data for 47 individuals over 1979 to 1988. And the variables we have here, charity is the sum of cash and other property contributions toward charity, and income, this is your gross income, or this individual gross income, and price is 1 minus the marginal tax rate. So you could think of this as the opportunity cost of giving a charity. Age is the dummy variable. Remember, age is dummy variable that equal 1 if the taxpayer is over 64. MS is the marital status, so it takes the value of 1. It's another dummy that takes the value of 1 if the person is married. DIPS here, or DEBS, is the number of dependents. Okay, so the idea here is that we trying to see the effect of the marginal tax rate on charitable charitable giving, or we want to estimate what we can call the charity function. So what determine how much you pay, or an individual would pay for charity. Okay, so on these we believe that these are the important variables that may explain the behavior of giving charity. Okay, so we have now data for both dimensions. We have data over time from 1979 to 1988 and across different individuals. So our subjects here, or our objects here, are individuals, are people. Okay. So this is like a snapshot of the data and how it is organized. We have subject 1, which is individual 1. This is the data over time from 1997 to 1988, and we've got data about how much they pay in terms of charity, the income. Price here is 1 minus the marginal tax rate. Age, again, is a dummy variable, so it's not age 0. It's 0 means that he's not above 64. Okay, so he's not a retired person, he's actually a young person. Again, or younger than 64. Marriage status 1 if married, 0 otherwise. Number of dependents, this is just the number of how many dependents. Okay. Have you noticed that before? So the first person had 2 dependents in 1979, and then they became 1 after that. Don't know what that means. I mean, maybe he had, just moved out. Yeah, yeah, get married. Yeah, that's right. You're right. Okay. Anyway, so this is how. This is just a snapshot of the data. Something that I didn't discuss, which is very important, which we're gonna discuss in terms of this example. We didn't differentiate between balanced data and unbalanced panel data, and we didn't explain what we mean by short panel and long panel. This is very important because it has some implication for your estimation. So what sort of methodology is more appropriate? It would probably depend on what sort of data you have. So the data we have, the data set we have is balanced data because we have the number of time observation T is the same for each individual. So what we have here in this example, so we have 47 individuals and we have data that cover 10 years for all these individuals, each one of those individuals. So that's why we have a balanced data. So if we had a missing observation where we have the time observation, the number of T is not the same for all individuals, that means we have unbalanced data, panel data. So on the other side, if we get short panel because N is larger than T. So we have N 47, N is the number of subjects, the number of units, and it's more than the length of the data or the time element in the data, and that's why it's called short panel. If we have long panel, that means T is greater than N. Okay? And as we'll see next time, this is very important to decide which model or which sort of estimation. So if you have, for example, T dimension is large, if you have long panel, then you have to worry about issues related to time series as well, like integration, whether the data is stationary or not, and we go back to what we did last 2-3 lectures. Okay, we'll think again, and this is something we'll cover next lecture when we talk about panel configuration. Okay, and again, this would be relevant if we have long panel. Long panel meaning that you've got T, large T, and small n. Okay, so this is just terms that are important when you deal with important to understand when you deal with panel data, because these might suggest different sort of estimation method or procedure. So I just put some naive way to think about this data set again, about what we saw now. So why don't we look at, someone can say, okay, we understand that we said the simplest way is to do the pooled regression, but we'll think before even more in a more naive way than that. So we'll say, why don't we look at have individual time series of charity function. So for example, individual 1, I have one regression for individual 1. Okay, to see how much or to model how much he give for charity over time from 19 whatever to remember when the data starts. So for over the 10 years, so we had 10 points. Okay, so again, basically you will have all this regression for 10 data points. It's not really very meaningful. We have very few degrees of freedom if you have 10 data points, and this again will neglect information about other individuals' charity contribution, because you will have a regression model for each individual separately, and this will not, that you're losing so much information because you're ignoring any information including the data set about other people at the same time. So you could do it the other way. You could look at cross-sectional charity function, where we in time t equal 1 we just have an OLS estimation of 47 observation. This will neglect the dynamic, because the charity giving could have changed over time as well. How that changes over time, the cross-section model of these, or individual cross-section model of these, will ignore this fact. So it's not going to capture this sort of dynamic behavior of the denominator variable. So go back to what we said before. So the simplest way to do the summation is to think of a pooled regression. So pooled OLS function, or a charity function, that means we have 47 individuals, 10 years. That means the total number of observations 470. So we ignore the fact that we have this 470 coming from 47 people, so we just ignore that fact. We ignore the fact that this is over time, so we neglect the dual nature of the time series and cross-sectional data, and we estimate the model. And that sort of modeling that would assume that these coefficients will remain constant across time and across section. So we don't try to model any heterogeneity here or any change of across units, and that's why it's called constant coefficient model, and that's the pooled one. So the other option we discussed is the fixed effect model, and we said we could use the least square dummy variable to estimate that, and again that would allow for different intercepts. And we can also use the within estimator, which we discussed already, but I'll show you an example how to do it in the views. And the third possibility, so just ignore the first two, because the first two I said these are very, very naive, and we ignored those. So we've got three possibilities here: the pooled regression, the fixed effect model, and the random effect model. And again, the random effect model here in this case will assume that the intercept values of the 47 individuals are random drawings from a much larger population of individuals, and that is what that explains why is it called random effect model. Okay, so let's now look at the first one, the pooled regression, the pooled or less. So what would we have here? CIT, this is our dependent variable, the charity given, so how much charity they give, individual one give in time, individual I give in time t. So that's how you read it. And these are the independent variables. Age, we said this is dummy variable that takes the value of 1 if the person is more than 64. Income, this is the gross income. Price is 1 minus the marginal tax rate. The dependents, this is the number of dependents. This is the marital status, another dummy variable that takes 1 if the person is married. And I here goes from 1 to 47 because we have 47 individuals or 47 subjects, individual in this case. And T is from 1 to 10. We have 10 data for 10 years. The important thing here is that we get the subscript IT, that's fine, but with the constant intercept is beta 1. Do you remember what we call this model? Constant coefficient model, because we assume this is not going to change. It's the same for all, yeah? It's one size fits all. Okay? Is that what they say? Yeah? But that's a way you could think of this model. So beta here, beta 1 doesn't have any subscript because it doesn't change. It's constant for all. Okay, so we'll assume that the regression, this regression satisfy all the assumptions that we make about the classical linear regression model. And but before we go to the estimation. And that's something very important for you to, like the way you think about, not just about your assignment, about any research you do, you just need to think about what is my per expectation for these variables, okay? How would these factors determine charity given? What should I expect? So if I go back to the model, so what would you expect about age, for example? Is it the beta 2, would you expect it positive or negative? Positive. So if you are more than 64, so you're likely to give more for charity, and that sounds true. The same with income. So if you have more income, that means you're more likely to pay, or you would pay more in terms of charity. This is the as I said, this is the opportunity cost, because this is not the marginal tax rate. It's 1 minus the marginal tax rate. So if the marginal tax rate increases, that means the opportunity cost of giving charity will be lower or will be less. That means you're likely to give more. So we would expect beta 4 to be positive. Number of dependents, if you have more dependents, you would because it's not the tax rate, it's 1 minus the tax rate. So the price here is, yeah, that's 1 minus the tax rate, okay? You're right if it was only the tax rate. So, but 1 minus the tax rate, you could think of it as the opportunity cost of giving a charity, because if the tax rate increased, if it's higher, that means 1 minus would be smaller, so the price that would be less, and that means the cost of giving charity is less. So you should give charity or you'd be expected to give charity if that increased. So the number of dependents, obviously, if you have more dependents, or number of dependents, so if you have more people rely on you financially, then you would be expected, yes, to pay less charity. So this would expect that this negative. The marital status is something that we could argue about. So, so if you're married, okay, would that make you pay more for charity or less? I'm not sure. Oh yeah. Do you count that as charity? Charity begins at home. Yeah. Okay. Anyway, so these are this just the expectation. As I said, we could think of this in different ways, but the most important one, because this is what we're trying to estimate, or this study was trying to estimate, it's trying to estimate the effect of marginal tax rate on charity given. So we should think of the price variable here as a representative of the opportunity cost of giving charitable contribution. So the higher the marginal tax, the lower the opportunity cost. That means we would expect people to give more in terms of charity. So let's go back to the main story, the pooled regression. How would you do that in eViews? It's very straightforward. In eViews, you just quick estimation, and even if you use the command, the way we do it in the seminars. So again, it's ls. This is the estimation. This is the estimation method, least square, and you include all the variables. So you start with the dependent variable, and then constancy, and then age, and the rest of the regressor. And this is the estimation we have. Sounds sort of okay. So we have charity as dependent variable. We have 470 observations, and it seems that the estimated coefficient come with the sort of sign that we would expect. So age, for example, is positive and significant. Income is positive and significant. Price is positive as we would expect and significant. Number of dependents, again, is actually this is not what we expected, because we expect if you have more dependents, that should be negative sign. So you would be expected to pay less, but it is significant. But again, this sort of model could be misspecified because it doesn't take into account any heterogeneity among these 47 people. Okay, so we've got 47 individuals that are very different from each other. Again, there could be an issue as well, but as I said, when we have a short panel, probably autocorrelation. I mean, you can correct with autocorrelation. We'll see how now. But yes, that's true. But anyway, in this just to show you an example of pooled regression. So we just ignore the fact that we have the 2 dimension, and that's why I show you this command line here. So in this the specification of this equation is very straightforward. That we did exactly the same thing when we do least square estimations. We didn't think of or we didn't consider that we have 2 dimensions in the data, the cross-section and the time element. So the other way to do it, so this is the pooled OLS. It's very straightforward, as I said, but it's likely to be misspecified, and I'll show you a way to test for that. We did this before, but I will show you how to do it, how to use it in this context. The fixed effect least squares dummy variable. We explained that before, that we should include dummies equal n number of the number of cross-section units. Okay, so what we have here is this is the general model where we have this. This is the constant. Now is different from the constant we had with the pooled OLS. If you remember, when we put the pooled OLS estimation, this didn't have any subscript. Okay, so we didn't allow for the constant to change across units. But with the fixed effect model, we allow for this, and this is how you see it. So just think of this beta 1i. Just think of this as alpha plus mu I. That's the new constant that we allow to change across units. This is the subject or individual specific effect. Okay, So that could be something related to religion, education, something that is not included here, but it's subject specific. It's constant over time, but it varies across units. Okay, so it's subject specific or individual specific. So the way we did this, we explained this before. And how we do this, we can add dummies. So these are the dummies here. So to estimate this model using the least square dummy variables, we added dummy variables from D2 to up to D. It should be 47 because I dropped D1. Okay, so I dropped one variable, one dummy, one group, D1, because this is my my benchmark, or this is my what I compare with, because I have a constant. So I kept beta 1 here. So I think I dropped the first one. So that means that should be, if I started with D2, that should be 47. But anyway, you got the idea. Should you drop only one dummy variable to be your reference or benchmark category, and this is what you're gonna compare with. So to do this, and in eViews, it's very straightforward to do this. All what you need to do is just to use the fixed effect model. So where do you find this? So you go to panel options, and then you choose how to treat the cross-section units. So you treat them fixed effect, and that's what's happened here. So this is the estimation, and again, we've got the same. It's very similar, except for the number of dependents became negative. That's what we expected, negative sign. So we expected that. It's still not significant, but again, it is at least with the sign we expected this to be negative. So this is how to do this fixed effect model. So the way I told you, like, we can actually test whether which one is performing better, or explain the charity giving behavior better than the among these, or between these two methods, or two models, pooled OLS or fixed effect using the least square dummy variables. We can use the restricted F-test, the one that we did in the first lecture. So it's very straightforward. If we think of the pooled regression as the restricted model, because it neglects the heterogeneity effect and it doesn't take it into account, and we consider the fixed effect as the unrestricted model. So you can do F-test. So this is R squared from the unrestricted model. This is R squared for the restricted model, and M here is the number of parameters excluded, which is the 46 dummy variables. These were the one that we exclude from the pooled regression. So the pooled one, the first one, didn't include these. And K is the number of estimated parameter in the unrestricted model. So if you do this, very quick exercise, very simple exercise, you got the value of statistics is relatively high, which means that the fixed effect is superior or perform better than the pooled regression. And this is something we expect in a way. So you don't really need to test for it, because we actually expect that, because we take into account the heterogeneity, unless if it's really a very homogeneous group, but it is something that is unlikely to happen in reality. Okay, that you would have like even if you have two brothers who are raised in the same house, and you try to model their charity given, they are different. Yeah, they are not the same. So they are not. It's very difficult to have this sort of homogeneity where you don't need to model heterogeneity explicitly, and that's why I said in most cases you would expect, or we should expect, that the least square dummy variable to be superior to the pooled OLS, just because the pooled OLS doesn't account for heterogeneity. Okay, doesn't model heterogeneity, or doesn't take it into account. We talked about the limitation, because we need to add more dummy variables that cost us degrees of freedom, and etc. And this is again just to jump this one. So to do the fixed effect, the within group estimator, is very straightforward. So the idea is to demean the variables. So this is the new regression equation where we have CIT. This is the charity given in from individual I, or in time t, minus CI bar. This is the this is the average, the time mean variable. So if you do that, you will get you'll see that there's no dummies here, there's no constants, everything dropped. Now all the variables that don't vary over time will drop from this equation, and that's what we will have. To do this in views is very straightforward. Again, I just want to show you how to calculate this if you want to, how to generate a new variable. So I'm creating a new series here called age d. You can give it any name. This is just a name for I give to a d-mean variable, just to know this is the d-mean variable. So I subtract age, so go back, so age minus, so this is exactly the equation. So I'm saying age minus the average of age by subject. That's what I'm trying to say here. So this is at means by age is the variable I want to calculate the age for, and by subject, so I want to do this for each one of the subjects, and I do the same thing for income and price, so all the variables in the model. And when I run the regression, so I still use the LS method or least square method, but rather than using the charity, I'm using charity d. This is the d mean variable. Rather than using than age, I used age d, and by mistake I added this c, because we expect that this c to be dropped. But let's say if by mistake I added it, what would happen? Okay, so you remember when we do that, when you run the regression for d-mean variables, the dependent variable by construction, it's actually it has mean 0, so it's actually very small, it's 0. Okay, because it's d-mean. So what's happened here? Again, I'm not going to discuss this in more details because just we're running out of time, but if you notice, this is very, very small numbers. It's nearly 0. So it doesn't matter if you add it or not, because it's going to be very, very small or 0. Okay. So this is the within group estimator. You can, to deal with some with the issues with the efficiency, you can estimate the robust standard errors. The only reason I want to show you this is just how to find this in views. So it's very straightforward. When you go to panel options, you will see how to treat the standard errors. So you can obtain the robust standard errors if you follow the if you take the white procedure. This will produce the robust standard errors. The last one, which is the again this is the same. We're following the same example, the random effect model. So we explained this before. So this constant here will depend on this epsilon I. Epsilon I now is different from mu I, because this is going to be determined randomly. And the way we introduce this is the composite error term, which is WIT here. It's exactly everything exactly the same except this one. The assumptions behind the composite error term, or this cross-sectional error term, the epsilon I. And in views, we already explained this. In views, all what you need to do is just to change the how you treat the cross-section. You treat them as random effect model from panel options, and this will give you the random effect, the summation for random effects model. Okay. The last one is Hausman test. Hausman test is very straightforward, very easy, because in views, after you do the estimation, you can go to view menu and then fixed random effect testing, and then you choose correlated random effects or Hausman test, and these are the results. So basically what we're trying to look at here, there is no the null hypothesis that there are no differences between the random effect and fixed effect model, meaning if you accept that, then we would prefer the random effect model, but if we reject that, we would prefer the fixed effect model, which is the case here. So that means in this case we should have the fixed effect model, because the probability value of the statistic is very small, meaning that we reject the null hypothesis. That means the fixed effect model will be more preferred to the random effects model. And as I said, so if we didn't reject it, that would have mean that we should use the random effect model. But in this case, because we have very small probability value, that means we have to we reject the null hypothesis, and that means we should use the fixed effect model. If you remember, I said the random effect models is more appropriate under certain conditions, but if these conditions are not valid, then we'll have to use then fixed effect model. Or we could use some sort of instrumental variables, because the main issue here is the correlation between this part of the error term and the one of the regressors or the regressors. Then we could try to find instrumental variable to represent those regressors that causing the issue, and then we estimate the model using instrumental variables. And this is something we hope to cover later on this module. But anyway, for now, if we reject the null hypothesis, then we will. If we reject the null hypothesis, we prefer the fixed effect model. Okay, I'm just laughing because I know you're waiting for this moment. You're waiting for me to finish. Okay, any questions?